All right, so we now have an understanding of where electrons might be located in an atom. We talked about the idea of orbitals, so now how can we specify what electrons are in what orbitals? And we're going to use something called an electron configuration to do that. In electron configuration is fairly simple on its face, and what I mean by that is it's just going to be a series of numbers and S and P's that are going to tell us where the electrons are located in any particular atom. Here we're talking about helium. If you look at a helium on the periodic table, it has an atomic number of 2, which means 2 protons and then 2 electrons. So we have 2 electrons in helium, and if we were to say where those 2 electrons were located, we'd say where they were in the 1s orbital. Remember, the 1s orbital is the most stable s orbital. It's the one that's closest to the nucleus. And there are 2 electrons in helium, and both of those electrons are located there. So we tell a lot of different, or give a lot of different information in this electron configuration. We say number 1, that was not, it was just ironic number 1 because there's a number 1 here. But number 1, it tells us what the energy level of the electron is. How far away from the nucleus can we find the electron? It tells us which orbital, what shape of the region of space around the nucleus we might find that particular electron at. Remember, the s orbital was spherical, or shaped like a ball. And then we've got the 2 here, and the 2 tells us the number of electrons that are located in that particular orbital for that particular atom. And so we can sometimes try to determine what the identity of the atom might be just by counting up the number of electrons, and we're going to see how that goes later. Here, there are 2 total electrons in this electron configuration, so it's got to be helium. So we're going to look at a little bit more complicated one here in a second. And in this one, the electrons are located in a number of different spaces, a number of different regions. So this is sort of like that analogy that we were talking about people living in the same house together for long periods of time, like all of us are doing right now. And there are 3 different rooms in this particular atom. There's the 1s room, the 2s room, and the 2p room, 2p rooms. And this particular atom has 7 people sharing those rooms. And so where are they located? So we've got 2 electrons in the 1s orbital, that spherical region, and then we've got a 2s orbital that's got 2 electrons in it. I want you to notice that the s orbital, there was only one way that we could arrange that or orient it, one type of s orbital, and each orbital, no matter what, whether it's an s, a p, or a d, or there actually is something called an f, which is very complicated, which we're not going to talk a lot about, but any single orbital can only hold 2 electrons. Now, where this becomes complicated is something like the p orbital, because remember we said we could orient the p orbital 3 different ways, along the x-axis, along the y-axis, or along the z-axis. And so along the x-axis, that p orbital can hold 2, and along the y-axis, that p orbital can hold 2, and along the z-axis, that p orbital can hold 2. So the p orbitals can hold a total of 6 electrons. So we've got 2 electrons in the 1s, 2 electrons in the 2s, and 3 electrons in the 2p. So if we were trying to figure out what the identity of this particular element might be, we can take the number of electrons, and that will help us try to figure that out. And our number of electrons in this case is going to be equal to 2 in the 1s plus 2 in the 2s plus 3 in the 2p, or 7 total electrons. So what element on the periodic table has 7 total electrons? All right. How do you find it? Well, the atomic number tells us the number of protons, which in a way, if it's a neutral atom, will tell us the number of tells us the number of protons, which then tells us the number of electrons as well, if the atom's neutral, and this would be nitrogen. And so that would be the electron configuration of nitrogen, just a short, little, concise configuration that tells us where all the electrons are located. And we want to try to understand how we might be able to go about writing that for any element on the periodic table. And you're going to see there's a progression that we're going through here. We're going to talk about where the electrons are located in atoms, and then we're going to move next to where electrons are located in compounds or molecules, more molecules than compounds. And we're going to call that process Lewis structure, and you probably never thought of a Lewis structure if you've taken chemistry before. You certainly never thought of it as a way that we can tell where the electrons are located in a covalent compound, but in reality, that's exactly what it is. So for us, when we're working on atoms, we want to determine the order in which the orbitals will fill. So that's sort of the challenging part. Once we get that part, we just have to determine the number of electrons the element has. We've done that before. We're going to start putting electrons in the orbitals. All right, we have an idea of how to do that. That's not a terrible thing to do. And then we're just going to stop putting electrons into orbitals when we have placed all the electrons into the electron configuration. And that sounds so much more complicated than it really will turn out to be. It just sounds complicated until we do it. And I'm going to tell you the worst part of it, or the hardest part of it, is going to be this first step, determining the order in which the orbitals fill. And I say that because I'm not one who likes to memorize. All right, so I don't like to memorize at all. So this part may involve some memorization for you. All right, now we say things like to be in low energy situations. So the orbitals that are going to fill first are going to be the ones that are the lowest energy. So if we talked about the idea of the s orbital, one s orbital being the most stable or the closest to the nucleus, it is that way, all right, because it's the lowest energy. That's where electrons will go first. And the next orbital that they want to go to is the 2s orbital, because it's the next lowest energy. And then the third highest or the third lowest energy is going to be the 2p orbitals. And remember, there were 3 different orientations of them, so there are 3 of them. How many electrons can each of those orientations of a p orbital hold? 2. 2 can go there, 2 can go there, 2 can go there. Then the 3s, and then the next is the 3p, and the next is the 4s, and then the 3d, and the 4p, and the 5s, and the 4d. And if you put that all together, you can write it out as a long string of orbitals in terms that goes from lowest energy to highest energy. So 1s is first, 2s is next, 2p is next, 3s, 3p, 4s, 3d, 4p, 5s, 4d. And generally there is a whole system that you can go through to learn how to write this out. I'm going to be honest, I don't think it's that important for us, especially because you're going to be sitting there using your notes whenever you take any exams or quizzes for this kind of stuff. So, I would just make sure you got that written down, understand why the electrons fill in that particular order, and that will be good to go with that piece of information. And then we're going to use this to then go through and write electron configurations. We're going to start with lithium. All right, so you may want to start looking for lithium on your periodic table. I'm trying to determine how many electrons that lithium might have. And you should find lithium's got 3 electrons. All right, so we know the order in which the orbitals fill. 1s, 2s, 2p, 3s, 3p, 4s, 3d, blah, blah, blah. All right, now we've got lithium and its 3 electrons, and we're going to start filling from the low energy to the high energy end. And 2 electrons can fit in the 1s. Why only 2? Because only 2 electrons can fit in a particular orientation of an orbital. All right, so 2 go there. That means we've already filled in or given 2 of the 3 electrons of lithium to that orbital, so we only have 1 left. It goes in the next highest orbital. So for lithium, the electron configuration would be 1s2, 2s1. That would be how we would read it. What it means is 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Now I want you to go back and think for a second. All right, we're going to start tying some things together. Lithium, what ion does lithium like to form? All right, take a look at your periodic table. Take a look at how many spaces away from the noble gas column. Lithium would be, and you find it's 1. It's an alkali metal. All right, so it wants to lose 1 electron. Which electron does it lose? Ah, well, suddenly there's this 1 electron in the highest energy orbital for lithium. That's the one that it likes to lose. We're going to call that electron a valence electron. And so it's cool to see how all this stuff ties together, and that's just gonna accelerate a little bit. Now, it turns out that electron configuration isn't the only way to look at things. Remember this idea that, when we put 1s2, that's signifying that there is a region in space where an electron's located. So it might be useful to be able to say, okay, here are where the electrons are located in this particular atom in a graphical way. And so we're going to use what we're going to call an orbital diagram to do that. An orbital diagram is just going to draw out all of the orbitals that might be relevant. So for lithium, that's the 1s and the 2s, and I put the 2p here just to show contrast with an example that we're going to see here in a second. We're going to look at oxygen next. And so there are 2 electrons in the 1s, and the way that electrons work is that they are like little tiny magnets, and they're going to have a magnetic field vector that's going to point one way or another. And so, think of about a magnet. It's got a north and a south pole, a positive and a negative end to it. And so the way that these electrons line up is so the positives and the negatives can be right next to each other, that the north and the south poles of each of the little magnets can line up just right. And so the way that those 2 electrons go in that 1s orbital is one will be pointing up and one will be pointing down. So we specify electrons with arrows. And then the 2s only has 1 electron. It goes in arrow up. All right, we call that spin up in the chemistry business. So we have 2 electrons in the 1s, 1 spin up and 1 spin down, and we've got 1 electron in the 2s that spin up. All right, so orbital diagram, another way of giving an idea of where is the electron located in an atom. How about oxygen? How many electrons does oxygen have? If you're saying 8, after looking at the periodic table, you would be right. Okay, so we've got our order in which orbitals fill. 1s, 2s, 2p, 3s, 3p, 4s. Now we're going to start jamming electrons into those orbitals. Okay, so we are going to go with 2 in the 1s, 2 in the 2s, and then I'm going to stop right there for a second. And the reason that I'm going to stop is that these 8 electrons, I've put 4 in, so I've only got 4 electrons left. Now I've got the 2p orbitals. All right, I say orbitals because there are 3 different ones. Each one can hold 2 electrons. So the 2p orbitals can hold a total of 6 electrons. Well, we don't have 6 electrons. We only have 4. So all 4 go in that 2p orbital. And I know I've got some of this other junk here. The animations and stuff don't work with the way that I'm printing these pages out because I just feel like it's easier for me to communicate with you all this way. So the electron configuration for oxygen would be 1s2, 2s2, 2p4. I have 2 plus 2 plus 4, 8 electrons. That would be a neutral oxygen atom. So that's the electron configuration for a neutral oxygen atom. You can do that. Electron configuration isn't bad once you start to see it. What about the orbital diagram? What does the orbital diagram look like? Well, we've got the electron configuration, 1s2, 2s2, 2p4, 2 electrons in the 1s, spin up, spin down. 2 electrons in the 2s, 1 spin up, 1 spin down. And then we've got the 2p electrons, all right? And now this is going to be a strange way in which these electrons fill into these orbitals, all right? So what we're going to do is we're going to say for the 2px, it's going to fill spin up. And then for the 2py, it's going to fill spin up. And then the 2pz, it's going to fill spin up. I'm actually going to write this out so that you can see it. And we're going to end up with the same thing. So if I were going to fill the 2p and I had 4 electrons to fill in, I would fill 1 arrow up, 2 arrow up, 3 arrow up. But that's only 3 of the 4 electrons that go into that p orbital. So I've got to put my 4th one in. It comes spin down. Does it matter to me whether you know whether each one is X, Y, or Z? No, I could really care less at this point whether you know that. Is it important for me that you can get the electrons filled in the correct orientation in the orbital? That is important, okay? That's important for us to understand. So that sort of, gets us to the point where we can understand electron configuration. You may well know some shortcuts for doing electron configuration. That's perfectly fine. I want to talk about just 2 of those in this video, in the remainder of this video lecture. First, I want to talk about neon and chlorine. So if we write the electron configuration for neon and chlorine, all right, you'll notice neon is 1s2, 2s2, 2p6. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. And you'll notice that part of the neon electron configuration and the chlorine electron configuration are similar. Now, why are we picking on neon here? You may already have some idea of why that is the case, but neon's right over here, last column in the periodic table. Remember what chemical family that is. Those are the noble gases. And remember, those are the number of electrons that all the other atoms want to get to. So neon, we're picking on neon because it's a noble gas. And this particular electron configuration shortcut that you might see is called the noble gas shortcut, or shorthand. So if we look here at neon, or at chlorine, we could say, okay, it's got the electron configuration of neon, the closest noble gas to it, or at least the closest one behind, not in front of it. So it's got the electron configuration of neon plus 2 3s electrons and 5 3p electrons. So we could say that the electron configuration of chlorine was the electron configuration of neon plus 2 3s and 5 3p electrons. So you might see electron configurations written in this way, where this shortcut using the noble gases would come into play. And what you would do is, if you were going to say, okay, let's imagine we're going to do bromine. Bromine might be, all right, the electron configuration of argon plus 2 4s electrons, 10 3d electrons, and 5 4p electrons. Okay? And you might notice this periodic table actually has some color coding to it. That's because the blue ones, the outermost electrons, are in s orbitals. The pink, the outermost electrons, are in p orbitals. The yellow, the transition metals, the outermost electrons are in d orbitals. And then we talked about the idea of there being f orbitals as well. These green, looks kind of gray on the picture on your screen. These ones down here, the lanthanides and actinides, the ones that we don't worry about a lot, they have their outermost electrons in f orbitals. Okay? One more thing to talk about, or one more thing that we should know, and that is the idea that we've been talking so far about neutral atoms. What about the idea of a fluoride ion? Fluoride ion means that we have fluorine, but it's gained 1 electron. So that would be 10 total electrons, 9 plus 1, all right? And so that would be the same number of electrons as neon, which is exactly why we said fluorine wanted to gain 1 electron and become a fluoride ion. So if we look, how do we fill out the electron configuration? Well, we start filling electrons in. We've got 10. 2 go in the 1s, 2 go in the 2p, and then 6 go in the, 2 go in the 1s, 2 go in the 2s, and then 6 go in the 2p, because there are 6 spots, 6 electrons left. That gives us 10, 1s2, 2s2, 2p6. Now what did we just say that looks like? All right, so if we go back, it looks like neon, 1s2, 2s2, 2p6. So fluoride ion has the same electron configuration. It's what we call isoelectronic, has the same number of electrons as neon, so it's going to have the same electron configuration. So here's where it breaks down the idea that we might be able to actually figure out what the atom is, because we would predict this as neon, but really it's fluoride ion. And so, all bets are off when we start talking about ions and electron configuration and trying to identify. So that's electron configuration. We're going to start next thinking about, how do we get electrons to, or how do we get light out of an atom? Or out of a compound, and it's going to have to do with electrons jumping back and forth between these different orbitals. Okay?